So we're going to do carboxylic acids and esters. And the email I sent you, assuming you all saw that your grades are posted for your celebration, and the average was higher, which is awesome. And I did post a video talking about carboxylic acids and esters that I normally would have done in class, but since we lost a week. So do watch that. It talks, there are two purposes of it. One, it actually might make more sense after. It is about 40 minutes, and it talks about examples of these, which we'll see tonight. The other purpose of it is you do have class presentations, and so you need to pick your molecule. And when we'll take a break at some point, because this is going to be our longest class of the term. You can email me or you can talk to me, and so we all have to have a molecule picked. I'm hoping by this weekend. You can absolutely change your mind, but that's the purpose of this video. If you're still having trouble, we talked about a lot of the spices, so several people pick those, and I'm making another video hopefully tomorrow that I'll be posting that is about nitrogen. So our lecture topic next week is going to be the amines and amides, which is nitrogen, and half of you end up picking a compound that has a nitrogen, and so that will be a shorter video. And then there is actually another video I posted, and it's only 5 minutes. It's probably my shortest video of all time, and it's what's on the board behind me, which is for the lab this weekend. We're in the 8th week, so lab 8, you are going to do a flow chart, and so it is of the QA lab that you turned in from last week. And the biggest thing with the flowchart is to have fun, let your creative side out. And there are some post-lab questions, but it's just a short video, and I talk about what's going on. This is not complete. I stopped at some point, and yeah. All right, so let's talk about carboxylic acids, and then we'll talk about esters. These are always taught together, like ketones and aldehydes were. So they both have double oxygens, and that's actually key. So they both have that double bonded oxygen, and then they have this other oxygen. Something that we've seen before, but I don't know that I really emphasized it, is this R. When you see this R, that just means carbons. So they call it an alkyl group, but that just means it could be a methyl, it could be a propyl, it could be a pentyl, it can be 50 carbons. But the key for carboxylic acid is this double bonded oxygen and then an OH. And then after 2 or 3 pages, we'll get to esters, which the only difference is that hydrogen. They're called carboxylic acids because they are acids, and we'll get to that on the second page. So they are always at carbon 1. So here we go. Those of you who are here, here's your first bonus question. What other functional group always has to be at position number 1?
Aldehydes?
It is. Is that Tiara? She's on it. Yeah. You had a work day. That must be why you're awake. Everybody else is asleep. We'll put you here under the fire. All right. So aldehydes also had to be at number 1. I did want to point out something because it was probably the most missed point on the celebration. In a cyclo, it is a cyclohexanone. It is a ketone in cyclos, even though it's at number 1. And an aldehyde has to always have a hydrogen. And carboxylic acid always has to have this OH with the double bonded O. And so that was, you can ask me later if you have a question. So we'll do the first one together, and then I'm going to pause and give you a chance to try these, or actually, yeah. So bute means 4. Now, one of the things is you can draw it. So the carboxylic acid is on the left, which is what a lot of students do. Traditionally, this would be my first carbon. That's my double bonded oxygen. A lot of times we draw it actually on the right side, and this is an OH. So the O does not count. So this is 1, 2, 3, 4. So but and then butane, the AN tells us it was all single bonds. And then the oic acid is how we end it. I did want to point out something because we run into it actually on the next question. That is an alpha. The font that I chose made the alphas look funny. This is an old nomenclature way that is only used with carboxylic acids. So the Iupac is where we number, and number 1 is the carboxylic acid. So 1, 2, 3, 4. In the old form, alpha means the carbon next to the carboxylic acid. So how they used to number it is this was the alpha, this is the beta, and this is gamma. And so the alpha carbon, beta carbon, gamma. So alpha means the same thing as 2-methyl. When you do this, the P is, of course, para. So hopefully you remember that because it's benzoic acid. And benzoic acid is going to look something like this, where you have the benzene with that one. I'm going to give you, actually, let's go ahead and draw these, and then I'll give you a pause. So benzoic acid, you would draw your benzene, and you can do every other double bond. But again, I like the circle. So you may know why I like the circle over showing the double bond. Because they're not really double bonds. They are actually 1.5 bonds. You can show the carbon, or you can write it as a zigzag there, and you have a double bonded O and an OH. And then para means 1 and 4, or they're across from each other. So the benzoic acid is always at carbon 1, and then the ethyl would be across from it. So we'd have our ethyl group there. To do this one, the pentanoic acid, so 1, 2, 3, 4, 5. And so this position is our alpha. And so that's what this one would look like. And then the last one, as they may remember, I talked about it with form. What would be the actual, this is the common name of formic acids. They may know what the Iupac name would be. So it's 1 carbon, and so it's methanoic acid. Nobody's watched my video. Or you're all just being shy. It's actually the very first slide on the video. Is form is 1 carbon, and it means ants. And so when you squish ants, they actually give off formic acid. So it would just be the 1 carbon acid. And the thing that's unique about this one is since there's no carbon there, it would have a hydrogen. So it's kind of a funky, right. The other comment, before I give you a chance to draw these, and maybe you already have, is you're not going to do this ever, but in case you see it, I did it like this because you will see this out there. This does mean a carboxylic acid. I talk about this in the video. You will never have oxygen connected to another oxygen. When that happens, it's extremely reactive. Oxygens don't want to bond with each other. And so this is just another way of saying our butanoic acid. It's kind of the lazy person's way of showing it. So this would of course be carbon 1, 2, and you can go on from there. So I'm gonna give you like 5 minutes to try them. These, you can at least try sketching something. Some of you are like brilliant. I think it was Tiara like aced them, and there was somebody, or no, actually it was Emma. I was thinking she must speak with the gnomes because she like got every single one perfect on there. I'm gonna pause, assuming I know how to pause. And numbering is, so I started that one, 1, 2, 3. And anyway we go, we're going to get to 5. And so we want to go the direction, we do want to go this way because it gives us smaller side groups. So we have an ethyl and a methyl. So we'd have 3 ethyl You guys have come a long way in these 2 months. Because I remember trying to teach that every time actually in the second week, and it's such a confusing or an interesting rule. So 3-ethyl, 4-methyl, and then we just say pentane. We drop the E and put on oic acid. We never put a 1 for the acid because it has to be at 1. So on the next one, when you have, this has 3 total, we don't give numbers. It is, we say the whole word propane, and then we say dioic acid. So the di means it's a double acid. So why don't I have to say 1,3? Like when we had alkenes, when we had dienes or di anything, we always had to put the numbers. Why don't I put numbers with acid? And it's not just because there's only 3 carbons. Whenever it's a dioic, you don't give numbers. Well, acids always have to be at the end on the, and so if it was a decane dioic acid, it would have to be at 1 and 10. So acids always have to be at the end positions just because it is 3 bonds. It's a double bonded O and that OH. All right, the next one, here's our 1, 2, 4, 6, 8. So it's just octanoic acid. And again, it is important to get that AN there to show we have all single bonds. And then this is benzoic acid. And we do have to say, this is there. So we could say 2-methyl, or what's the letter we want? The O. So ortho, or just O-methyl benzoic acid. All right, and then our game. So pentanoic acid will make R5. You can do it this way. So part of our problem is initially it was saying this is 5, 4, 3, 2. Put the methyl there. And of course, the mistake is it has to number from the other direction. So this has to be number 1, 2, 3. And so our methyl is at 4. So it should just be a 4-methyl, and we don't put the 5 there. So it's just 4-methyl pentanoic acid. Yeah, these are pretty tame. I don't know if I reposted the syllabus. So your study set, it will be in the next folder. I'll open it tomorrow or tonight when I remember. So your study set for carboxylic acids and worksheet will be due Monday, and then the esters will be due Wednesday. And then there'll be new lecture notes for Monday. All right. And so benzoic. The benzoic acid has to be at number 1. There is no place for the ethyl there. So the ethyl has to be at any other position that you want to put it at. It doesn't really matter. I'm going to put it at number 3. You could put it at 2, 3, or 4. You cannot put it at 5. You may know why it can't be at 5.
Is it because it makes it a 2?
It would make it a 3. Because we'd be at 3, 4, 5. So yeah, you had the right idea. Right, so if we 1, 2, 3, 4, 5, so it's the same as this. And again, this number could have been a 2, 3, or 4, or OM or P. Right, and then propane is just 3 carbons. And then beta would mean, again, this is alpha, this is beta. So here we're going to put an isopropyl, an isobutyl. And the reason I said isopropyl is that would be the other most missed thing on our celebration was just to always be careful. It can help to underline. Isobutyl has that extra kink, right? Before you branch off. And so that's the butyl. So a lot of you are really good at mixing those two up. So this would be 1, 2, 3, and then we have 4, 5, 6. So this is our only side group, which is at number 5. So we'd have a 5-methyl and hexanoic acid. And hopefully those of you who like did one like this and then said 5-methyl pentanoic acid giggled at yourself when you, or whatever, pentanal, whatever it was on the celebration, because I could see you clearly numbered things right, and then you wrote a bizarre name down there, and it's fun to see what our mind does when we get into those modes, even if we don't feel like we're highly stressed. Is there any questions on this page? That wasn't too bad. All right, so we go to the properties page, and so carboxylic acids, boiling point. So our rules for boiling point were this. We had H bond. We had the ones that were polar, but not an H bond. So H bond was the OH. We had the ones that were polar that had the oxygen, but not the hydrogen. That would be another common mistake. So those would be the 3 most common mistakes on the celebration. So something like an aldehyde has an oxygen, but it's not H bonding. So that would fall in this middle category. And then we had the non-polar ones, which were like the ones that are carbon and hydrogen only. And so this is our hierarchy. We're going to add higher ones today. So where are carboxylic acids going to fall on this hierarchy, and why? Everybody's hesitating.
They're going to be higher because they have an H bond and an oxygen.
Yeah, they actually are above this list. So yes, Christy got that. It was a trick question. It's actually even beyond that. It's that they actually always form these dimers. And so you get this thing where they flip and they H bond to themselves. This is more than what you have to know, but because of that, they end up being like double in size of what you think they are, because they end up always H bonding to themselves. But because they have both an H bond and polar, they have the double oxygen. Since they have 2 oxygens, they have the highest of what we've talked about. That's going to change in the next 5 minutes, but they are up above because they have an H bond and 2 oxygens. So that was our acids, just write acids. So they're above. The H bond ones were our alcohols. Solubility, it's the same rule we keep saying. So yes, to a point, because so yes, it's a vague rule. Let's say up to 6 carbons. And let me write Christy's name on the board before I forget. All right. So yeah, they're, and again, we're talking about water soluble when I ask solubility. So they do tend to be, they tend to be a little bit, yeah. It's not that something's more soluble or less, we're usually yes or no. This is their key. I should have done this one in pink. I can still do it in pink. They are acids. They are weak acids, but their name is that they're a weak acid. They are stronger than phenol, but the test for them is the litmus pink. If you had phenol, there would be a way to distinguish them, but I'm not going to ask you that question. So if you have those test tubes and you're asked to sort them, you pull the acid out first by just doing the litmus test. I do want to comment that this question keeps coming up on all the last 4 study sets. So on the celebration, the ketones, there were 2 answers I accepted. The answer I was looking at was the ketone is the last tube standing. The ketone was the one that wasn't going to react with anything. There was one or two of you who did that first test that was from the lab, the Dnph test, which I accepted it because I was like, oh, they actually listened to my video when I was like high on ether. You'd have to be careful though, because you'd have to first pull out the aldehyde, or you'd have to pull the two of them out and then separate the aldehyde. But I accepted that answer. So they are going to react with NaOH. I wanted to, acetic acid, does anybody know how many carbons that has? Again, it's in the video on the very first slide. And why? It's 2 carbons. So you would call it ethanoic acid, but everybody calls it acetic acid, and it is the word for vinegar. And so acetic acid would be drawn like this. And the reason acids are acids, carboxylic acids are acids, is because of the double oxygen. Alcohols are neutral. Alcohols only have the OH, and so you cannot, they are not acids nor bases, they are neutral. And so this hydrogen, because of the double oxygen, there is this extra pull. So oxygen's pull, that's where the word polar comes from. And the oxygen, that second oxygen is really pulling, and it makes it really easy for this oxygen to be pulled off. So if we react it with a base, so sodium hydroxide, and we're going to see this reaction in 2 pages, this hydrogen is going to come off and combine with the hydroxide. So the reaction we're going to get is water. And then the other piece that we get is the carboxylic acid is still there, but it's no longer an acid. It just lost its hydrogen. It has a negative. And the sodium is a positive, and it comes on. This is a new category, and this is a carboxylate salt. This is called sodium acetate. So I always show the positive and negative. You don't have to. I show the positive and negative to make sure you realize this changed the game. This is now ionic. We have a positive and a negative. That's the word salt means ionic. It's a question for you. See if any of you remember from this. This will make my ego go up if it's somebody who had me for 104 answers. Why did I write the sodium first before the acetate? Nobody's answering. So we always say cation. Remember, cats have paws. Cation and then the anion. So the carboxylic acid loses the hydrogen and becomes the anion, and it's going to attract. This is usually I use sodium. We might run into a potassium, so it's usually either going to be sodium or potassium. It could technically be any cation, but this changes our game. Before I go into that, I want to make sure I finish the last question here, which is odor. And there's reason there's a goat on here. Talk about it, the second slide of that video that you really should watch because it has a lot of information on it. They smell like goats. And I commented this to my kids 3 weeks ago when we were out at somebody's horse barn, that this is considered one of the carboxylic acids, and then when we get to amines, are considered the 2 most awful smelling compounds in general. They put them into a thing, they don't tell people what it is, and they have them smell it, and these are extremely unpleasant. So that was another question I wanted to make about the test tube thing. When you have 5 test tubes and you have to sort them, some of you just said smell, it smells unpleasant. You know, that video, which a couple of people made a comment about, that it was a little choppy. These things, to me, they stink, they reek, and I really was pretty loopy from being around that in lab. So just imagine if you were, they are all unpleasant. So you would have to tell me more specifically. It's the thiols smell like a skunk. And as unpleasant as that is, it's not actually the most unpleasant. That's like a serious warning. And so some of the kids told me goats, they actually like the smell of goats. I have never gotten that close to a goat. I've been around goats and haven't really gone up and sniffed them. You can think of it as dirty socks. I don't really smell dirty socks either. But how do you spell socks? That's a good choice. It's also, yeah, so they're just not a pleasant smell at all. Carboxylic acids are just like somebody who hasn't showered for like a week or something, or you go and run and you just had a really great run, but it was a really hot and humid day. And when you can smell yourself and you're like, I need a shower, that's a carboxylic acid. So our sweat is carboxylic acid is in there. I don't know which one. That's something I've ever really been interested in, but that's the smell of them. And it's not a pleasant smell unless you're a dog. I think dogs really like that smell. Now, when you make it ionic, the odor is none. These smell like, go smell like table salt. What does table salt smell like? It really doesn't have much smell at all. I mean, it might have a little bit, but it's not smelling like dirty socks. And so the other thing that happens when you make it into a salt is the shelf life becomes, you know, I'm not going to say infinitely long because everything has a shelf life. It becomes excessively much longer, much longer. Much is not a big enough word for this, but much longer. Shelf life, carboxylic acids do not have a long shelf life at all, like really short. They're very unstable. Aldehydes are probably the most unstable in ethers, but the salts are very stable. And so like Vincent's here and in his clinic, so we call it like Novocaine or different things like that. It's actually, if you ever look at the label, it's actually been made into the salt of them. Now, that's not the best example because those are nitrogen compounds, and so that's a different game, and we're going to talk about those next week. But that drugs almost always will be found in the salt form, whether it's the sodium salt or the chloride salt, which we'll run into next week. Possibly one of the most famous of these is monosodium glutamate. So glutamate was actually a dicarboxylic acid, and then if you pull one of the hydrogens off and put a sodium on, they call it monosodium because they didn't ionize the other side, and then that's the umami flavor that people crave. And for me, it gives me headaches because glutamate is actually a neurotransmitter, and it's an excitatory neurotransmitter. And so unless you grew up with it in the cooking, a lot of people, like, I don't go out for Chinese food ever because it triggers headaches. Nothing causes headaches except apparently this stuff. But if you're somebody, and then there's people who say it's a myth that people don't get headaches and stuff. Anyway, that's a fun topic too, MSG. And it's why they make them the all-you-can-eat Chinese buffets, because you can't stop eating with the MSG and that umami flavor. But that would be a carboxylate salt. So that's this category here. The pH. So somebody else, what's going to be the pH? So you have three choices: acid, base, neutral. And why? You may want to take a gander at it. So we had an acid and it lost its hydrogen. So those of you had me for Chem 104, this is like one of the things we ended with. Remember, we had acid plus base. So we'd say acid plus base. And on the other side, we made the acid became the CB, which was the conjugate base. and then we'd call the water, excuse me, the conjugate acid. Maybe, maybe not. And so this actually is a base because it lost its hydrogen. And so what's going to happen to litmus paper? Not going to turn
Would it
pink.
stay blue, or would you need to use the
It
pink?
turns blue. Yeah, you take blue, you take pink litmus, and so it turns litmus blue. So technically, when we say litmus pink, you use blue litmus paper, and it turns blue litmus paper pink. And in this case, then you would take the pink litmus paper and stick it in, and this would turn it blue. All the rest are neutral. There would be nothing would happen. Or there's usually now universal paper that has different colors based on the pH, but this becomes basic, and so litmus would turn blue. All right, here's another chance. It's like trick questions here because the game changes with carboxylic acids and then the salts. Boiling point. This goes back, this little chart that we just made, for those of you who had me for Chem 104, it should be looking like, I know you don't remember this, but it was about halfway through the term when we did intermolecular forces. And so we had the London dispersion, which are the nonpolar. We had the dipole. We had the H bonds. We had a double H bond is really what's going on there. And then the highest of them all was ionic. And so all of these things, all of these that determines, this is again our hierarchy, is the attraction. You have an attraction of a positive for a negative. And so the more the dipole, the more the dispersion of the electrons, the greater the attraction. So since this is ionic, it is the highest. It is exceedingly high. In fact, it's a solid. These guys are solids because they're salt. So the word salt, when a chemist uses the word salt, does not mean table salt. It means an ionic compound. So these guys are solids at room temperature. They're going to be our highest boiling point. And so and solubility, they're ionic. There is no limit to their solubility. You don't need to count carbons. So even the big ones, if it is ionic, it is soluble. So absolutely loves water. You don't count carbons. They are going to be soluble. They're going to have the highest boiling point. You could easily, they would turn litmus blue. They would be stable. They wouldn't have a smell. And I talk in the video about fatty acids. Fatty acids are obvious an example of carboxylic acids, and so we see the double. That's this. I don't know why they ionized it in this picture. In our body, fatty acids aren't going to be ionized. Everything else is, but this is a saturated, so that just means that they're all single bonds. So this would be an alkane. And then here we have the double bond. So the kink is a cis double bond, and that gives us the kink. When we talked about alkenes, we talked about it. It's just now we're putting this ending on it and making it into a fatty acid. And then there's the cis versus trans, and I talk about that a little bit in the video. Questions from this page. And again, the reason for the study sets is to help you then go back and refine all of this. But this is actually a big page. The boiling point, the carboxylic acids are higher than anything we talked about. And then once we make them into a salt, which you will see the sodium or potassium there, it makes it even higher, quite a bit higher. Acid versus a base. And again, the carboxylic acids are soluble to a point, like everything else that had oxygen. Once you make it ionic, doesn't matter how many carbons you have, they are soluble. They love water. unpleasant smell like a goat, and no smell. All right, we're going to talk about esters, and then I'll give you a chance to try naming, and we'll take a break if you want to. All right. So esters is, I didn't want to dress like a goat today. You can't really see how I'm dressed, but I had flowers. I wore flowers. I had my flower skirt on, and I forgot to make my printer print in color. But those of you who could print in color, there's a reason flowers are on this page. Esters smell beautiful. So whereas we had carboxylic acids, which smelled like goats, these guys smell like flowers. They are the smell of flowers. So your essential oils, which are very fragrant, a lot of them are esters. There is like half the state of New Jersey is based on making chemicals because our sense of smell is our dominance, is so dominant, even though it's not one of our strongest. But if we blindfold you, so we take away sight and have you smell something, we can make you have, there's places they can make you feel like you're in a McDonald's. Like like when I'm on my bike and bike past the fast food places, the aroma from there is always overwhelming. But these smell like flowers. The other very fragrant one, does anybody remember what the other fragrant one was? That was the aldehydes, but only the ones that got to a lot, and ketones also, but you had to get to a lot of carbons. All right. So, yeah. Also fruit, flowers and fruit. And so we usually would do a lab next week where you guys would mix different chemicals. That's what our next page is about. And so you're going to do the lab. You're just not going to get a mix of chemicals. You're going to just have to do it on paper, writing it out, and then match using Google, and then some other stuff. So the esters are always oxygen in the middle and a double bonded oxygen. So there's always one carbon. This carbon has the double bonded oxygen and the O. So you always name the alkyl side group first. What that means that carbon with the double bonded O is always carbon number 1. So wherever the double bonded O, and I just realized that my thing, the formatting is all off. This pictures on this page are unfortunate because I always made that my side group was on the right. It could be on the right or left. You cannot count across the oxygen. So this is 1, this is 2, and this is 3. This is the alkyl side group. On this one, this is 1, this is 2. This is my side group. On this one, this is 1, this is all on this side. You can put a line, the oxygen side. This is my alkyl side group. And so that's what I mean by the alkyl side group. So like on this one, this is a methyl. On this one, that is a, so you know what that is? It's a carbon with 3 CH3s around it. That is a tert butyl. Pretty sure I'm talking to myself tonight. It's all right. And that's what snow does. And when the college decides to say, hey, let's just take you all away for a week. Lost my audience. So that's a tert butyl. And so that's why you guys are going to do class presentations. So I don't have to keep talking. And then here we'd have 1, 2, 3. The oxygen you never count. So we're counting the side that doesn't have the double bonded O. And so this is a propyl. When we name an ester, that's always the first piece. So like on these, the cyclohexyl, the ethyl, the isopropyl, that's a piece on the other side. So now this part is our main part with the double bonded O. So how we would name this, we would say the methyl first, and then we say our other side, And we call that the carboxyl side. So when you have a oxygen and a double bonded O, just like a carboxylic acid, basically the methyl, the terp-butyl, and the propyl replace the hydrogen that would have been there on the acid. And so this is now propano, and we say 8. So the ending for esters is O8. All right, our next one would be the T-butyl. And then 2 carbons, you guys would all say ethanoate, and that is perfectly fine. So again, O8 is the ending for esters. Most people just say acetate. That's the common name for 2 carbons. So acetic acid becomes acetate. And so you'll see that you can call it ethanoate. It's if I use the term acetate that you recognize that means 2 carbons. All right, and then this one we would say the propyl first. And then this side it is a benzene, so it is benzoate. The ester has to be 1 carbon removed because the double bonded oxygen cannot be on a benzene ring because it would have too many bonds. So that is our idea of the ester. So we're going to take like a 5 minutes. You guys can try drawing these, or you can take a 5-minute break. You can also try down here the raspberry, pear, and banana. Try naming them. And if you want, if you're really an eager beaver, or you can take a break, you can even go to this page, and because we're going to name all the ones on this page. So I'm going to pause us. You can try those, or you can go take a break, and we'll come back.
Sounds good.
All right. So that was the carboxylic acids. Here we go. Esters. So again, esters have the carbon. Actually, it was on the first page, showed it. So we have the carbon with a double bonded oxygen. You have an oxygen, and then you have another carbon group there. That's what the R means. And then you can have anything. The R just means more carbons over here. The reason they show it with an R and R dash, they could be the same, they could be different. So when we do this, it doesn't matter which side you draw it on. You can draw the cyclohexyl on this side. Then that would have the oxygen attached, and then the carbon double bonded oxygen. That is carbon number 1. And then propane. So we'd have carbon 1, carbon 2, carbon 3. So if you show carbons, I'll do it also with the zigzags. The thing I wanted to point out is that our carbon 1 in our ester, there's no hydrogen on it. It's filled with 4 bonds, so it never has a hydrogen there. And again, the cyclohexyl is the side group. It can be shown on the left or right. It's shown on the other side of the oxygen. If you want to keep showing it as zigzags, the oxygen and then the cyclohexyl, you can show however you like. That's just, you just flipped it. And again, that's 1, 2, 3. Again, it doesn't matter. This is what makes it an ester. All right, ethyl hexanoate. So you can do the, so this would be 1, 2, 4, 6. That's our hexanoate. There's our oxygen, and there's our ethyl. And yeah, you can show it on either side. You can show carbons. Some people like to write carbons in. But again, this is our ethyl, is on the other side of the oxygen. All right, benzoate is, we have a benzene, we have our double bonded oxygen, and to our oxygen. So that's our benzoate, and then our isopropyl. This is where the different colors probably is helpful. I've never had different colors before, and I just realized I was off there. And so that's my isopropyl. It is, again, this piece that's on the other side of the oxygen, where I showed on the left or the right, is, yeah, always written at the very beginning, always written with a YL as a side group. It's not given a number because it's not on a carbon. Carbons get number, oxygens do not. You cannot count across an oxygen. All right, properties. They are polar. They do not H bond. Why? They lost that OH. So they are polar, but they're not going to H bond. So soluble, only small ones. So yes, they have oxygen, but because you got carbons on each side, they tend to get pretty large. And so only the really small ones, like down here, the raspberry, pear, and banana, they're too big. They got too many carbons going on. Actually, all the ones on this page are probably, this first one might be water soluble, the methylpropanoate. All right, boiling point. So we'll just do that, less than 6 carbon. Boiling point versus an alkane, esters are higher because they're polar. Alkanes are non-polar. Alkanes are just carbons and hydrogens. All right, boiling point versus carboxylic acid, esters are lower. And that's because they do not H bond. So they're in that middle category, polar. They have 2 oxygens, so versus another polar, they're probably going to be higher because of the double oxygen pool. And really their key property is they are fragrant. They are flowers, perfumes are pretty much always esters, the essential oils, and fruits. And so that's why I got a star. That was the last test. I didn't show it on here. Is a test that distinguishes esters. Was the one that got blood red. It was one of the unknowns. I don't remember which one right now. But we're going to go ahead and give the Iupac name for these scents, just because it's a good thing to do, and I'll be consistent. This is the side opposite, not with the carbon double bond. So that's my side group. So what kind of side group is that? There's 4 carbons, and it's in this funky formation. Anybody know? That is isobutyl. And then what would the other side be called? I don't know who said that.
It was Christy, but I already got a point.
Oh, that's why I thought it was you. That's why I was just checking to see if it was somebody else. So this other side, you guys would probably all say methanoate. You can think of it because they're the smell of our fruits that we want to eat them. So that's why they end with 8. But 1 carbon is usually called formate. So most places would call it isobutyl formate. And all right, pears. Let's do pears is green. This is our side group, just 3 carbons in a row. So this would just be propyl rated up above. And then this side we have 1, 2. So propyl ethanoate or propyl, anybody? The
Acetate.
other name? Yes, acetate. So propyl acetate. So bananas. This guy gets a name that this side group, this was our side group, that was the propyl. This side group is a side group we don't know how to name. So you would not be asked to do this without me telling you what that's called. I'm pretty sure it's called an isopentyl. or an isoamyl. I don't know why, but I'm pretty sure this is isopentyl. And so you have to be able to name that side for you guys to do it as one word. We never did the pentyl side. There's I think 6 or 8 different ways you can draw a pentyl, and then this is 2 carbons. So isopentyl acetate or isopentyl ethanoate. All right. I'm pretty sure that one comes up in the lab and I give the name. And so I'll put it as, yeah, we'll worry about it when, not this week's lab. That will be next week. This is also a key thing to star. That's why I have stars all over it. It's neutral in pH. So that litmus test is actually really important because very few things have a pH other than neutral in organic chemistry. And so our carboxylic acids, that's why they're called acids. They're weak acids, but they do definitely change litmus paper. And then their salts become a weak base. Esters, though, because they lost that hydrogen, they don't have any influence on pH. Everything else we've done has had no influence on pH. There was one other thing, though, that was a weak acid. Does anybody remember? You all had it on the test. Everybody got that question right. The phenols. So phenols, remember that was the other one we did the litmus test with. Phenols are just barely acidic. And so we don't really run into them again. All right, let's go ahead and get the reactions over with. So there's 2 reactions that we're going to do. We're either going to make an ester or we're going to break down the ester. So I guess 3 and then saponify. All right, so the key here is this up here. The carboxylic acid plus the alcohol is going to give you an ester plus water. So this is our key here. And so the alcohol, that was the side group on the ester. That was what I kept writing in blue. I should have written it in blue. So let's go ahead and draw them. When you draw these, the key is you have to draw so that the OHs are pointing towards each other. So since I'm drawing the methanol second, we would draw it like that. The propanoic acid, we have to draw its OH pointing. So, and then double bond to oxygen. So that's 1, 2, 3. So the OHs have to point towards each other. So one of them is an OH and one of them is an HO. And then you do the cowgirl chemistry or cowboy chemistry or whatever you want to be. And so you loop out the water molecule. I'm going to do it correctly. It doesn't really matter. You're going to pull off an OH and an H. And so this drives most students crazy because the OH comes off of the acid side, but it doesn't matter. One side loses an OH, and we're going to put it together. So you still have 3 carbons and the double bonded oxygen. And then you're going to go to the oxygen and the alcohol group. So what was the alcohol becomes the side group. It's called now just a methyl. And then the other side we call propanoate. So some of you, usually a significant number of you, actually find that it's easier to do from the words, that methanol propanoic acid, that you go, oh, it's going to make methyl propanoate. There's always a few people who actually see it from the words and then draw it. All right. Let's do our second one. So just make your OHs point towards each other. You can draw the carbons in, or you can do zigzags. Most of you all do zigzags, so that's why I'm doing zigzags. The key is you have to draw them as an OH and an HO. So we draw our acid, and then this one is connected to benzene. And we can put our plus sign. I forgot it here. And then you can loop your, and put them together. So I think I did draw it right. All right. So there, oh, you can also say plus water if you like. I always forget that. Organic chemists tend to only show the organic chemical part, but you're still going to have your benzene ring. You still have your carbon double bonded oxygen. And then, and it's up to you if you like using two colors. I think it's really helpful. So this is ethyl benzoate. That's it. And it's called esterification because we built an ester. So the alcohol is this group, the ethyl or the methyl, and then the other part was the acid. All right, so we're gonna do one more, which is, actually we just saw it on the previous page, but it was actually something I thought was really cool because it's the smell of bananas. It is also a pheromone that is found in bees, the exact same molecule, and it's what honeybees specifically use. It's the pheromone they give off to say danger, something's happening. And so I thought that was pretty cool. So acetic acid, so let's go ahead, that means 2 carbons. So again, ethanoic acid, so 2 carbons. And then this guy would have been, if we drew it as 1, 2, 3, 4. So 1, 2, 3, 4, and then that's what it would look like. So that was the one we had on the other page. It's also known as isopentyl, I'm pretty sure. But I might be wrong on that. I have to look it up. All right, do our reaction. Count to 10, give you a chance to either write it down or to finish the reaction. And then you can even name it. We're counting to 10, Rocky. Rocky's here to say hello. Say hello to everybody, Rocky. All right. Rocky is going to help us. You don't have to circle your water molecule. It does help some students to circle it. And we get our oxygen, and then 1, 2, 3, 4. So again, this is number 1. The oxygen doesn't get a number. So just be careful of that. Oxygen, sulfurs, nitrogens do not get a number. It's only carbons that get a number. And then plus water. And the name would have to be the isoamyl. And then acetate. Again, it's the smell of bananas, or the pheromone that honeybees give off. All right, questions? Yeah, go, Rocky. So now we're going to do the opposite. Oh, the picture in the middle is about triglycerides. I think I mentioned it in the video. And it's how fats are made. So in our body, we store excess of any calories. If you eat too much protein, if you eat too much sugar, if you eat too much anything, other than whole foods that have a lot of fiber, because there's no way you can actually eat too much of them. The amount of carrots you would have to eat, your body can't physically hold that many, or the length of time it takes you to chew them comes out crazy numbers. So we get this backbone, which is glycerol, which has 3 OHs on it, and there it shows that pulls off the water. See, they're showing it. Interesting. Anyway, so we get this 3-carbon backbone here, and then fatty acids attached to it, and so that's a triglyceride. We're going to do the other reaction, which is hydrolysis. So we're going to do the opposite. If you take an ester plus water, you'll get a carboxylic acid plus and alcohol. So let's go ahead and do it. So the easiest thing is to always start at the end with benzoate. So you draw your benzene, and then benzoate means we have the carbon with the double bonded oxygen, and I just switched my colors. We'll go with green, and then you need an oxygen, and then your ethyl. So I'll make my ethyl in green because I just switched colors. You can't really see the difference in color. Do it in orange. So the water molecule, water is going to cut right there. So between the oxygens, basically. But there is a carbon right there, and that carbon stays there. So what you end up with is you have your benzene, and it still has this piece here, and you have to have something attached to it. So I'm just going to put a blank for right now. Some of you will see this. Everybody visualizes it different. It's a little funny doing it not on the board. And then the other side, I have the oxygen with the ethyl group, and it needs something attached to it. And so we're adding water. Water is actually an H and an OH. So one side gets the H. Let's do it in pink. Sorry. Blue for water. And the other side gets the OH. So you cut right here and you add an OH. So you get your H's and OH's pointing towards each other. And this would be benzoic acid. And ethanol. So don't make the reactions hard. You're either going to put them together or break them apart. The hardest part about esters is two things. We always learn about them in the 8th week. Having a week off from snow didn't really help because we get in a flow and we keep building on it. And they're just bigger. We just have this oxygen in between, but don't let that worry you. All right, we're going to do the same thing, but we're going to add a piece to it. So ethyl benzoate, same molecule. But we're going to cut it like we did, but then we're going to add NaOH. So a reaction, we get our benzoic acid. And so the easiest way to teach this is if you go with what we just did, but this OH plus our other one, which was our ethanol. The ethanol isn't impacted by this, but the whole point is this is a base. So you're going to cut it into the two pieces, and then you do an acid-base reaction. So the acid hydrogen comes off. You have a negative here, and then the sodium goes on. And so that's what would happen if you saw adding NaOH. So hydrolyze. So step one is you hydrolyze. So you do hydrolysis, which means to cut. So Jeremy was in my Chem 106, and so we did this a lot in biochemistry. There's really two basic types of reactions in your body. You're either using water to cut things or pulling water out to put them together, or oxidation reduction. They're really almost the two broad categories. There are other niche categories, of course. And then this is an acid-base reaction. This is how soap is made. That's why the picture of soap is there. And so that would be step 2 is the acid-base reaction. And so the hydrogen came off and we put the sodium on. So soap works because it has this area that loves water, and then it has an area that loves things that are hydrophobic. And so it surrounds them and makes them, emulsifies them is actually the correct word for it. And so usually I spend more time talking about this. Those who take Chem 106, we actually do a whole lab and we talk about, because this ends up being a very important thing, like for our cell membranes and stuff. Yeah. All right, we're going to go on though. So 2 pages to go. Let's see. All right. Let's talk about anhydrides and then we'll look at that other page. So anhydrides are that prefix an or a means without or no. And so this is without water. And so it happens when you have 2 acids. It can be 2 of the same acid or 2 different acids. But again, there's the water molecule and it pulled out the water molecule and you lose water. And that's what we get. So you're usually going to have heat involved too. So heat to heat off the water. They're extremely useful to use in lab. So in Chem 104, we do an aspirin lab. So you would have either watched me or your teacher, whoever you had for Chem 104 or whatever, a video of somebody using an anhydride. They do have a strong smell also. They end up then with 3 oxygens. So that's the anhydride part. So to name this, we just say, you name the acid, cyclohexanoic acid would normally be what we would say, but you put the name anhydride. If it is the same on both sides, you don't repeat yourself, you don't say the dye. I don't know why, I didn't make up the rules. So you would just say it one time, cyclohexanoic anhydride, and everybody knows that must mean it's the same on both sides. Like this is not isopropyl. This is 1, 2, 3. This would be isobutanoic. So, because it's got that extra elbow. So you can say isobutanoic anhydride. So that's if the 2 sides look the same. You can do an anhydride in which they look different. So you have your oxygen, you have your double bonded oxygen. So one side we're going to have propane. So there's 1, 2, 3. And then on the other side, you're going to have ethane. So 1, 2. And so that's what that one would look like. So if they're different on the 2 sides, you just say the 2 words, ending both of them with oic. So ethanoic, propanoic, anhydride. So I mentioned the aspirin. So this is salicylic acid. And if you take acetic anhydride, they're extremely reactive. They're extremely unstable. And that is because they want water. This planet is water-based. We're water-based for a reason. They're extremely unstable. And that's because they just want that water and they will get it from wherever they can. And so we see a reaction happening here. In the case of this, it's just going to cut it into the 2 carboxylic acids. So it's going to cut into the 2 carboxylic acids. So butanoic anhydride would mean you would end up with 2 butanes. I can do it over here. So you would have butane on one side and then butane on the other side. So 1, 2, 3, 4. I know it's, and then you just cut it into 2 butanoic acids. And it's up to you if you want to write it twice, or you can just say, I get 2 of these. Just we're adding water. And so you can cut wherever you want. One side will get the H, and one side will get the OH. The reason I mention it is it's not so much the anhydrides show up in our body, but there is something known as phosphate esters or phosphoesters and phosphoanhydrides. And I'm pretty sure you've all heard of ATP and also of DNA, and my other class we're talking about this, but these are anhydrides. So triphosphate is, so you see the double bonded O, O, double bonded O. So it really does look like that. It's just they're not showing the angles correctly. And then using water, whenever we use water to cut, we call that hydrolysis. So hydro means water, and this part here, lysis, means to cut. So it is really in digestion. Digestion is all about hydrolysis, cutting things into pieces. And so it shows up a lot. There's other places in our body that hydrolysis happens. So these are anhydrides. And then this piece here is the ester, because it's hooking up to a carbon. So over here, these are anhydrides. More, yeah. And then this is, yeah, so that's what ATP is. Any questions? Got one more page. This page has many reasons. One, it gives us practice. So we are going to go through, we're going to identify functional groups, and we're also going to practice giving them Iupac names. But it is also where I give my little talk. It's supposed to be either on Monday or last week about picking your organic molecule. And actually, I'm really proud because half of you have. I do want you all to have one by this weekend. You can absolutely change. I've had a lot of people change 2 days before our presentations. Our presentations are scheduled for the Monday. I don't know, of week 10. That must be the 8th, because Monday is the 1st, right? I think that's right. I might have got my days all mixed up here. So week 10, we're going to be presenting. We'll talk about it more next week, but that's why I want you, your papers will be due by the end of the week. Yeah, that's the plan right now. So we'll talk next week more about it, but that's why I need you to get a molecule. A couple things about your, you do need to have 2, I've mentioned this, 2 scientific studies. So you do need to talk about them. You should have a slide. And you need to be able to talk about it in your own words. And that might influence your topic. So if you pick a topic and then you can't find any scientific study on it, pick another topic and look for it. There's tons of scientific studies, or you might find, I picked this topic, Dr. Sherpa talked about it and sounded really interesting. And then when I looked into it, I didn't find it really interesting. And so you want to pick something that you're passionate about, especially if you have a connection to it, because often when we have that, you guys know, we just did those other presentations, when people had a personal connection and could talk about their personal connection to it, it made the presentation and also the paper much more interesting. You are doing both a presentation and a paper this time. And so the paper is, I think, like 4 to 8 pages. I'd have to look. There is in the folder, the syllabus folder, which is up by like our Zoom links in the upper left-hand corner of our Blackboard page, there's a folder that says syllabus, etc. There is a page there that talks about this. So the presentations are like before. There'll be like a 10-minute presentation, and we'll split into 2 groups. The paper though is longer, and so then the paper, but you'll have till the end of that week to get the paper in. So pick a topic, but before you just pick a topic, make sure you're going to find information on it, and information that you find interesting. And so like Kristen picked dopamine, and you could all do dopamine and you would all do a totally different paper on it, but she's the only one who gets to do that. And you can absolutely switch your topic. These are, I think actually somebody did this one last year, and it was after I had mentioned it here, and it was because her dog had seizures, and her dog, she went home after we talked about this and looked at her dog's medicine, and it was actually this. And she actually did an amazing presentation, and everybody absolutely, because everybody writes about it, everybody said it was her favorite, and it was because she was able to so personalize it and have pictures of her dog in there, and talk about it and how like they didn't know what to do with the dog, and then this medication actually became actually the dog was able to go about being a dog again. And so it was a really fun. That was before we all got quarantined. So we had a really fun potluck and all shared food, eating with our hands and stuff. And then a week later, we were all not allowed to be around each other. So let's go ahead and go through it. So this is valproic acid. So to name it, 1, 2, 3, 4, 5. To me, it looks like a frog. So apparently it's not famous for its smell or anything, but it's used for seizures. And yeah, I had another student who had, there's 2 different types of bipolar. And so he actually ended up doing, it was a really amazing talk. It blew me out of my seat because I had no idea, but he actually had been diagnosed with bipolar, not the full manic depressive, but there's another level of it. And so he actually ended up doing medication that he was on. He talked about it. It was my class that we only had 8 of us. And so everybody became really close in it. And it was actually really awesome. All right, so we would name it as Pentanoic acid. Almost all the acids have a common name. I talk about that in that slideshow. And again, that slideshow is if you're having trouble or you don't like yours. The next one I'll also talk, I know I do my molecule that I would pick, and I talk about some of the scientific studies. You want fun scientific studies. This side group is a propyl because it's 1, 2, 3. So we do have to put a number with it because it's an acid. So 2-propyl pentanoic acid. And so the functional group is a carboxylic acid. So if I asked you, I did say we're going to identify functional groups. All right. So the next one is a carboxylate salt. And there's 2 of them because calcium has +2 charge. So it's just 1, 2, 3. So we say the calcium first, because again, it's the cation. So cats have paws. Probably why Rocky came in here. And then this would be propanoate. We don't say dipropanoate because calcium has a +2 charge, so there must be 2 propanoids. But that must be choice B here, and apparently it's used in baked goods and cheese spreads as a preservative, because so sodium benzoate, if you have anything in your home that is in a box, food, if you look, there's a preservative, and it's usually sodium benzoate, especially, yeah, a lot of things have sodium benzoate in it. But apparently, if you're doing baked goods or cheeses, you can't use benzoate because it would interfere with yeast. It destroys the yeast. Yeast are small living beings. You and I are large living beings. There is a controversy if sodium benzoate is a carcinogen or not. So I've had people actually pick. You can pick if you want a topic that's inspirational, or if you want one that's going to be kind of a downer or something. But again, you want to find that personal connection to it. All right, C is commonly known as caprylic acid. So Capricorn is the goat sign. There's 3 different carboxylic acids that have either caprylic or something. So I'd have to count 1, 2, 3, 4, 5, 6, 7, 8. So 8 is caprylic. So octanoic acid again. Again, notice we don't count the oxygen, but it is carboxylic acid is our functional group again. And yeah, this is one of the anti-yeast for people with yeast issues. We'll often do caprylic acid. All right, this one's going to be a fun one to name because it's a dioic acid, so it's a carboxylic acid, but it's also got an alkene. So 1, 2, 3, 4. So it's going to be butene, so the ene, and then dioic acid. Now, we don't number the acids because they have to be at the 2 ends. And we don't actually number this because if there's only 4 carbons, the only place the carbon double bond can be is between 2 and 3. But there is a word that is missing. They may know what's missing from my name. Because this one is also 1, 2, 3, 4. This is also butene dioic acid. So with that, what is the word missing from both of them? It's a different word from each one. Remember way back, the first celebration? This is cis, and this is trans. These are isomers. They're actually both found, which is really cool. It's just the cis versus trans. The malic acid, I don't know as much about, but fumaric acid is part of the Krebs cycle. And this is something else I want to mention. It's something that shows up a lot next term. In our body, the acids are always ionized. And so they're always the carboxylate salt. And it's just what our body does based on our body's pH. And so this is correctly shown with a negative and that's why it says fumarate in the explanation up above. It's just its common name. That's and so when you find like citric acid, it's actually better as citrate. So a lot of people will take citric acid, but or ascorbic acid, vitamin C, it's actually, you should take it as the ascorbate because our body does better with that because it's already in the ionized form that our body wants it in. All right, and then this is actually really cool. So this one, tartaric acid, is what's found in grapes and bananas. And then if you add a potassium to it, I knew we'd see a potassium, that makes it cream of tartar. And cream of tartar is actually naturally part of fermentation of any of those fruits, of grapes and stuff, and then is used in baked goods by a lot of people. But let's go ahead and name it. So we get, this one's also going to be a fun one to name. It doesn't matter which way you numbered it. It's actually symmetrical on both sides. So it is butane dioic acid again. But we want the ane, and then we have the OH groups there. And so the acid is always gets preference for the name. When OH is a side group, you guys ran into this on the celebration we'd say 2,3-dihydroxy. We do have to put numbers because they could both be at number 2. So we're saying they're at 2 and 3. So 2,3-dihydroxy butane dioic acid. On this one, the difference would be we would start by saying potassium and then 2,3-dihydroxy. Oh, you know what? It has to be a monohydroxy butanoate. I don't know how you would do this. Butane, it's not a dioate. So I think we just say butanoate. And this is where, no. You know what? We're not going to name that one. You wouldn't have to name one unless the potassium was on both sides, because then it won't work. They get common names. Let's just move on. All right, aspirin and ibuprofen. I have, look, our favorite painkillers down here, and this is oxycodone. So if you want to do an opioid, actually, I had somebody, Hattie did a talk, I think it was 4 or 5 years ago, and she works up at OHSU, and it was just in the ICU, and it was basically about our opioid addiction, and then right after that's when I started seeing all the articles that our country is acknowledging that we created an opioid issue over the past decade of giving everybody so many pain medications. I've had several students who worked as CNAs, and they were saying it's just ridiculous how we just have drugged everybody. But aspirin, let's just do our functional groups. That this up here is our carboxylic acid. We're not going to be able to name these because there's too much going on. This is an ester. Because that's a methyl, right? And so this here is an ester. If we look at ibuprofen, this is our carboxylic acid again. And so both of these are non-steroidal anti-inflammatories. And so you could pick, you could pick one of them as your topic. Oxycodone, that is not an ester. There's only one oxygen. So that is an ether. And that is an ether. Just that oxygen there. This is a ketone. So double bonded oxygen. I picked this one on here because I wanted to point out this is not an ester. So I have a double bonded oxygen, and then I have a single bonded oxygen. And over here, I said, hey, I have a double bonded oxygen and another oxygen, like that's monkey in the middle. But here I said it was an ester, and here I'm saying it's a ketone and an ether. So I am right for a change. Why? What's the difference? It's your last chance for a bonus point tonight.
Is it because of the hydrogens that's bonded with the carbon oxygen?
No, it's not the hydrogen. So it's specifically why this and this, why didn't I make that into an ester? Does anybody see? Why did I make them two separate functional groups?
Because it doesn't have anything on the other side. The oxygen is already full.
There's 2 carbons here. Here, there's 1 carbon. So on the ester, the carbon has the double bonded oxygen and the oxygen single bond. It's 1 carbon. Here, these are 2 separate carbons, so it's 2 separate functional groups. It always goes back to the carbon. So those are really great tries. but it always goes back to the carbon. And so that's why I wanted to put that on there. And actually that was a really great try. And I appreciate that. Nobody else wanted to try because nobody could quite see it, but hopefully now, and that's why I actually put this picture on there, or these three on there. Is that different? This is an OH. I also wanted to put this on because these are really cool, and they do show up actually like morphine. Somebody picked morphine. I think somebody picked morphine. Yeah, somebody picked morphine. Heroin would be really. Actually, had somebody did, and it was an awesome paper. That is an alcohol. That wedge is saying that the OH is coming out towards us. These are three-dimensional. This is an aromatic ring, or it's called an arene. So it's kind of aromatic benzene. They combine into one word. And where we're going to be going on Monday is this group here is an amine. The nitrogens. And the nitrogens are really cool. It gets into some really fun possibilities. So if you haven't picked a topic yet, you can watch the video and see if that sparks an interest, or the one on the amines and amides, that always will probably bring up something that you're like, ooh, or even if you did pick a topic and you watch that and you're like, oh, I want to do that. That would be more fun, or it's something you can relate to. I wanted to point out this because this carbon here is hooked to the nitrogen also. So it's making this ring. There's a ring happening here with this nitrogen, this, and so it's showing it would be coming out of the paper at us in 3 dimensions. And so that's why they're showing it with this wedge. But these carbons here are part of the ring that's down below, and then this other ring that's got the nitrogen in it. So it's pretty cool. Yeah. All right. That was a lot of information. I'm gonna go ahead and stop. Unless somebody has a question for the good of the order, pick a topic. And you do have a lab. Before I stop sharing. You guys do have a lab. Let me see my view. Nope, it's not gonna do that. Nope. All right, we'll just stop recording if I can figure out how.